Okay, transmutation, anybody? What about the word mutation?
One gene changes makes it look different.
Gene changes and makes it look different. Good. It's the exact same thing in chemistry. Except we're not talking about genes, just leave it. So it's when one element, listen carefully, this is a real important word in nuclear chemistry. Transmutation is when one element turns into a completely different element. Regular chemistry, that cannot happen. I can't take sodium and turn it into chlorine. Doesn't happen. But nuclear chemistry, it actually can, because you're changing the nucleus. What's inside the nucleus? What? Say louder. Protons, neutrons. Good. That number over there, the blue number, the atomic number, is the number of protons. If you change that number, you're changing the element. Change that number, you're changing the element. So nuclear chemistry, you mess with that nucleus, protons and neutrons, you have a different number of protons. Let's say you're going to turn into a different element. So nuclear chemistry is unique, very unique. Anyone ever hear of alchemy? What is it? Turn lead to gold.
It's possible. Oh, he said it was possible, but it was ridiculously expensive.
Right, so yesterday in that video, if you saw it, it is possible, but it costs a lot of money, and you only get a little bit of gold, so it's not even worth it. And it's nuclear chemistry that makes it possible, not regular chem. Regular chemistry talks about electrons being transferred, taken or given or shared, right? That's really all that can happen in bonding. But nuclear chemistry is very different. That's why this is a different type of question. So transmutation. Now this question says natural transmutation, and obviously it's multiple choice, so there's only one answer. But I'm going to rephrase it. So there's two answers. Which two of these show elements transmutating? So turning from one element to a completely different element. Which two choices, don't say it, keep it in your head. Which two choices show elements turning into completely brand new different elements? Kristen, want to give me one? One. B and He turn into, transmutate into nitrogen and N. What the heck is N? It's lowercase n. It's not nitrogen, that's capital N. What's that mean?
Neutron?
A neutron. So boron and helium are helium are turning into nitrogen and a neutron. That's transmutation. Devin, what's the other one? Two. Carbon is turning into nitrogen and then getting rid of this thing. That's called a beta particle or an electron. All right? Look here. S and S doesn't change. Na, Na doesn't change. These are not transmutation. These are transmutations. Okay? So that's the easiest way to answer the regents question is by just looking at the left and the right side of the arrow, and if it's something different on both sides, that's transmutation. This is the natural one, number 2. That's natural. This is called artificial transmutation. Next week we'll talk more about that. You don't need to know that now. But anyways, that's a good regents question based on kind of like what you learned in the video, or what I was hoping for you to watch. Obviously, watching it once, you're not going to learn it. You have to watch things a few times, but we'll take notes next week, and videos and stuff will help. So anyways, that's that. I'm going to put that, actually, I'm going to leave that on. Now what I want to do is kind of break from the nuclear stuff. I just wanted to start class with that based on the video. Now we'll kind of backtrack a little bit before we move on. Okay, so London dispersion forces. Did I start this yesterday? I did not, right?
No.
Okay, so there's a bunch in the beginning of this, bunch of stuff in the beginning you don't need to know. He's going to explain a little bit, and I'm going to fast forward it. So this is London dispersion forces.
Later. But London dispersion forces are going to be attractive forces. These are intermolecular, between molecules, and they're going to be found in all atoms and molecules. So everything is attracted through London dispersion forces. Really important. What really develops them are uneven electrons. As the electrons are distributed unevenly, they create what are called a temporary dipole. Those are going to be a molecule that has a charge. It has a positive and a negative charge. These are going to increase as we increase the contact area between the molecules. Also, as we increase their polarizability, which is going to be the squashiness of a molecule. Generally, the more electrons you have, the higher this is going to be.
So you don't need to know all of this. You just need to know the dispersion forces increase with molecule size. We talked about that. As you move down the group, more electrons, more movement, therefore more of these temporary dipoles. And the animation he has is pretty good here.
Electrons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside.
This is actually a humongous, very important concept in like real life chemistry, AP chemistry we talk about all the time. The electrons of one atom are attracted to the protons of the other. That's why literally anything that ever happens in nature or in your life is because of that. That's not a crazy statement. Bonds are formed or broken because of that force and that interaction, and everything that happens is basically a chemical reaction. Even just thinking, you have chemical reactions going on in your brain. So that's a really huge concept there. So these electrons are attracted to those protons, these electrons are attracted to those protons, but the problem is the electrons are both negative, so when you bring 2 negatives together, they repel. So again, that concept explains a lot of things in real life. Dispersion forces are part of that. So when it's arranged this way, they're going to form the temporary dipole, but it's temporary. And that's what I'm trying to explain. These forces exist, but they're temporary with this type of force.
And so what this really is creating are 2 what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those 2.
Well, why is it temporary? Who was that? Because what keeps moving? Those Fox? I can't tell. There's a lot of mumbling going on. What keeps moving? Is that what you said? What did you say? I thought you said because it keeps moving. I mean, that's just what I want to hear. What keeps moving? Yeah. These electrons that were over here can move over here. And if they do, they repel the other electrons. There's no more force. So it's temporary. It breaks, forms very easily. Okay, non-polar substances do it. Last part of this here.
Fairly simple. It's going to hold them together. Now it's just instantaneous, it's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more electrons we can have closer to each other, the more of these forces we're going to find. So if we look over here at N-pentane and neopentane, they're both going to be made of the same atoms. But these ones right here are going to be looking more like a column and these more like spheres.
Okay. Ready? An interactive part of class. Hold your hands up. You like this? I'll have to show Taylor. So she's going to do this. She can interact at home. Okay? Now put your hands together. Okay, take them apart. Make fists. Put them together. Okay. Which scenario has more contact? More surface area? Flat hands or fists? Think about two balls, 2 basketballs or whatever, softballs, kickballs, whatever, dodgeballs. You put 2 basketballs together, they're going to touch, but a very small space, small area they touch. But if you were to cut those basketballs and take the leather and stretch it out and then put it together like your hands, there would be more contact. That's what he's talking about. These have more contact area because they're like columns, kind of like this, and then those have less. And what does that do with dispersion? The more contact, the stronger the force. The more contact, the stronger the force. So, I thought that was kind of cool. Kind of shows you some things. But moving on, that's dispersion. Dipole, I'm not even going to really let the video play because it's just this. Dipole interaction, what is it? It forms those dipoles just like we just saw, except these are permanent dipoles. Why? That's 8, no, it's that symbol that I've drawn.
You're doing 8s.
No, it wasn't.
Those weren't 8s?
That's an 8. I was doing this.
I thought those were 8s the whole time.
I thought you weren't just finished.
What does that symbol mean? No, for real, what does that symbol mean?
It's a sigma, lowercase sigma, and it means partial charge, which I've said over and over and over again.
So they weren't 8s?
No.
They weren't like +8, -8.
I didn't draw it. Listen, that's not an 8.
It looks
Come on.
like you didn't finish it.
I guess I can understand why you think that, but that would be pretty bad on my part.
It's all messed up.
I thought, yeah.
They are not
everything-
8s.
I gotta fix my whole notes now.
The whole time they're
I guess I apologize for not explaining that. It's I should have explained it. It's like a Greek symbol for sigma, but it's lowercase. So
That's funny.
that's not an 8. So all right, good. I feel even better. I showed you the video. Now we help not confuse you so much. Yeah, they're not 8. Sorry about that. Why is the Cl bigger than the H?
Because it's got more electrons.
More electrons. Good. And it's pulling. These two are fighting, sharing, but unequally. So Cl, right? This was the rock and Bree here, dragging Bree along. Okay, so H is holding on for dear life, but all the electrons are getting sucked that way. So this is partially negative, not an 8. Partially negative, partially positive. They're attracted. That's called dipole, and that's permanent. These dipoles are permanent, so that's a stronger force. It says weak, but it is weak, but it's stronger than dispersion, right? It's all relative. Yeah, you can have two things that are weak, but one's stronger than the other. All right, that's dipole. It's just more of the same thing from the notes, just a different way to see it, and I'm glad you saw it because now we're not confused. Okay, again, this one I'm not really going to play the video. This is that crystal lattice stuff I was talking about. That's salt. When you put salt in water, at first it just kind of sinks. But then it starts to dissolve because what happens is the water molecules will come into the crystal and literally rip it apart. Rips the crystal apart, and here's why. I'll show you the zoomed in version here. The Cl minus, and this is just review from our notes, but it's a better visual than my notes. Na plus, Cl minus are attracted to different parts of the water. Water has 2 hydrogens that are partially positive, and then the oxygen, the red, is partially negative. So the oxygens are all attracted to the Na, so they rip the Na away from the Cl, and then the hydrogens are all attracted to the Cl, rips the Cl away from the Na. The only thing this is missing is it's not 3-dimensional. There'd be another water molecule in front and then one behind. So it's always 6. Always 6 water molecules gang up on one ion, and they rip it apart from each other. So this explains why salt dissolves, molecule ion attraction or ion dipole. Either way, that's the same force. This explains why salt dissolves in water. And guess what happens when you evaporate the water? You know what happens. Salt's left behind because the Na plus, Cl minus get together again. So Na and Cl are attracted to each other, but water interferes with that. Water comes in, and because it's 6 on 1, Na and Cl have no chance. They can't break away because there's 6 water molecules surrounding them. And if you think of it that way, kind of like a gang of water comes in here and beats up the Na and Cl, but when the gang leaves, they can get back together. Sorry. All right, and this one I am going to play. Okay, so on hydrogen bonding, this is the most commonly tested force of attraction. Does anyone remember what is significant about hydrogen bonding, or maybe the elements involved besides hydrogen? Oxygen, good. So hydrogen with oxygen has it. What is it? Nitrogen and fluorine, right? Naph or uffin, right? So this is a pretty good video. It's a little blurry, I apologize, but it's a good one. And then after this video, I'm going to have you take out your notes. We're going to write a few things down in our notes about this that I haven't talked about yet, and then we'll discuss that demo with the water, and then we'll do the nuclear stuff. All right, here we go.
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule. Although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion dipole attractions in magnitude. In a series of similar compounds, such as these group 4A hydrides, boiling point typically decreases with decreasing molecular mass. This reflects the smaller London dispersion forces that exist between smaller molecules.
Okay, I was actually, I was not up here when period 2 was watching this. I was doing something else with kids from Earth Science Lab. Why I told you that, I don't know, but I guess I feel a little guilty now because I should have explained this to them. So this is showing dispersion forces. These are all nonpolar dispersion forces, and the y-axis is boiling point. So you can see the boiling point goes down, pretty low boiling points. You're going to see there's going to be another line with hydrogen bonding. Where would you expect the line to be? If it's a stronger force, would it have higher or lower boiling points? Higher. So you're going to see the line is going to be above it, right? So I guess I just feel guilty and explain that to them.
Note, however, that in the series of group 6A hydrides, although the same boiling point trend is observed for the heaviest members of the series, the boiling point of water is anomalously high because more energy in the form of heat is required to break the hydrogen bonds and separate the molecules.
So that was it. I'm gonna stop it. That's the gist of it. That I'm not really worried about you understanding these two lines every point, but bless you, hydrogen bonding really changes the graph. Bless you. So dispersion force is down here, hydrogen bonding way up there. So water has higher boiling point because of hydrogen bonding. So take out your notes. I want to write a couple things down. We'll talk about the demo, and then we'll do the nuclear stuff. Yes, sir.
I'll try to go to the bathroom.
Yeah, hurry up. You go every day this period, and you miss stuff.
Oh, crap. On X.
So get it. Okay, so under hydrogen bonding, I think that's where we left off in our notes, correct?
Yes.
Yeah, okay. All right. So I don't know if we wrote this already, but higher boiling points. We might have.
Yeah.
Higher boiling points. Okay, good. I'm going to write two words here. Capillary action. Capillary action and surface tension. Both of these you may or may not know what they mean, but they both are created because of hydrogen bonding. So surface tension. Edwin, can you check that? Is this getting this part of the?
There's a glare.
Yeah, it's kind
Or
of
can
glare.
you make it out? What's the glare? Windows?
Yeah, from the light.
Alright. Or can you make it out?
Yeah, I guess so.
Not.
I'll check in a second. Cohesion, adhesion is another two words here that we'll talk about. So I'm just going to talk about those briefly and what they have to do with hydrogen bonding. And then we'll get into the nuclear stuff. Oh yeah. I see what you mean. That help?
The next one.
Okay. All right, so higher boiling point, capillary reaction, surface tension, cohesion, adhesion. All right. So, what happened in the demo? I put the screen on the jar, filled it up with water, put the glass on top, flipped it upside down, slid the glass off. Water did not come out. Why did the water not come out? Surface tension. Good. Guess what causes surface tension? What? I know what you're saying. What causes surface tension? What are we writing it underneath in our notes? Hydrogen bonding, right. So the reason the water didn't come out of the screen or out of the jar because of hydrogen bonding, but that's too simple. That's like, that's just an easy answer. Let's get a more complex, deeper understanding here. If I took the screen off and I dumped the water out, or turned the glass upside down, jar, whatever, the water would come out. Water still has hydrogen bonding, but the big opening isn't going to get it done. You need little openings. So the screen, because it's a bunch of metal and mesh there, there's little tiny openings. What happens is the water, well, before I answer that actually, how do you think about it? If I took her water, is it empty? little bit, and we just splashed it on the window. Would all the water run down the window and make a puddle on the counter, or would some water stay on the glass and bead up? Would the water bead up, or would it all literally just fall off the window? It bead up, right. If you take a shower, it doesn't just run off of us. It beads up on us. If it rains, cars, right, trucks, whatever you want to imagine, it beads up. It doesn't all just run off. Most of it does, but it beads up. Why does water bead up? Hydrogen bonding, right. The water is attracted to itself, and it's attracted to our skin, cars, the glass, whatever it's on. So the water forms little bubbles because it's attracted to itself. That's part of it. It's also attracted to whatever it's touching through hydrogen bonding. So what does that have to do with the screen? It forms those bubbles, and because of the surface tension, the bubbles don't break. And the screen, I'm answering this obviously, the screen has those little tiny openings, and what happens on each little opening, the water bubbles up. Like if you were to zoom in, it would look almost like bubble wrap. So when you held the glass upside down, you'd have the screen, and then you see all these little bubbles. And the bubbles are pretty tight, pretty strong because of the forces of attraction. But you need something for it to be attracted to. That's what the little, the little like squares the mesh would create. That's why it doesn't come out, because there's small spaces the water can like grab onto that metal and form that little bubble, and it can withstand a lot of weight. But if you got a big opening, it's too big for the force to kind of span that whole area. So it's a pretty interesting demo. I'm talking about these two words the entire time I'm talking, because capillary and surface tension has to do with these, and so does capillary action. All of it's from hydrogen bonding. But what do these two words mean? What if I had a gecko and I just threw it on the wall?
It's stick.
Or if I had a gecko and just threw it on the ceiling?
Don't they have
Cassie
sticky
got
things?
mad at me this morning. She's like, "That's awful." I'm like,
They have-
"Let's
don't they have
assume
sticky
it lands
things on
with
their
its, its feet." touching it.
Hey, don't geckos have sticky things on their feet though? That is a bad
That's
example.
a chameleon. I don't know. I think some geckos might actually.
But don't geckos have the sticky things on their feet so they can actually cling to the ceiling?
Right. Geckos stick to the wall, stick to glass, stick to the ceiling. They have like these little hairs on their feet. Cilia?
You look at us like we have gecko at home.
No, but the name. Some of you might know what that's called. Anyways, guess why the gecko sticks to things? Hydrogen bonding. Very good, Ryan. Hydrogen bonding, yes. That's pretty cool. It's the same reason water beads up, is that geckos can walk all over the place.
Is that how Spider-Man works?
Yes. So, it's similar, right? Doesn't he have like little hairs or spiky things on his hands?
Nah, I think he just climbs.
No, but it's hydrogen bonding.
Yeah,
All right.
it's by
So
his hair.
back to this. Surface tension is the skin water has on it because of hydrogen bonding. So lizards or whatever can run on water, like little tiny lizards, right? You guys know what I'm talking about? You ever see that one? It kind of like does one of these things, right? Like really fast. It's kind of cool. Capillary action. What's that? Have you ever had blood taken from your finger where they kind of prick it and then they just kind of stick like a little, you may not have, like a thin glass tube and the blood just flows right into it? If you've never seen that, then you have no idea what I'm talking about. But a lot of people think it's the blood, so your heart's pumping blood, and they think because of that pumping, blood is getting pumped into that glass. That is not happening. It's not crazy. People might think that, but that's not what's happening. It's capillary action. And what is that? It's when a liquid, usually water, climbs a very thin tube or very thin opening. So if you had a puddle of water down here and you put a very thin tube in the puddle, water would climb naturally up the tube. Think about gigantic trees. Where do they get most of their water from? The ground. The roots. How does the water get to the top? Capillary action. Okay, there's I don't know the names of these channels, but very thin channels. Water travels up. Okay. Sometimes it happens if you're drinking something and you have a very thin straw, like those little red coffee straws. If you put that in whatever you're drinking, the level of the liquid in the straw will be higher than the level of the liquid in the glass. So you have the straw in it, and then the liquid will climb. This is why. Capillary reaction. So that's capillary reaction. Last thing, really important, is both of those are explained in the gecko by this, cohesion, adhesion. Yes?
I got a question. How come when you put a straw in like water or something, you put your finger on the top of the straw and you pull it up? How come the water stays in there?
Pressurization.
You're creating a vacuum essentially, and so I'll give you an example that might help. On top of everybody's house, you have like some pipes coming out, at least one of them. I don't know what the real name of it is called, but I used to work in the summers with a solar company and put solar panels on people's houses, and we call it the soil stack. And what that is the tube. There's a tube coming out, and it's usually above the bathroom. If you didn't have that ventilation and you flush the toilet, the water would not go down. It's the same exact explanation. So you need airflow for the water to move. Same thing with like the straw. Good question. So cohesion, adhesion, real quick, because I gotta get you going on this other video. One of them, I'm gonna have you guess. One of them means water is attracted to itself. The other one means water is attracted to something else, like glass.
Cohesion is itself.
Yeah, adhesion means it's attracted to like the glass or the walls of the tube. And then cohesion, water is attracted to itself. The way this works though, how it climbs, it's kind of cool. And think about paper towels. If I dumped my water on the floor and I took a piece of paper towel and I put just the corner of the paper towel in the edge of the puddle, would the entire paper towel be wet eventually? Yes, it would.
That would take like 10 years. The water would evaporate.
Yeah, it wouldn't dry before.
I want you to try this. Go home, pour some water on the floor.
I know, I will.
Okay. Do it on the counter though, all right? Not on the floor. So anyways, the whole paper towel will get wet. Why?
Because it's good.
Hydrogen.
Hydrogen bonding. It's capillary action. Inside the paper towel are all these little spaces, kind of like this tube, and the water pulls itself through the paper towel. Let's say we all went on a rock climbing adventure. Okay, and let's say, who is it? Isla is the lead. So Isla's climbing up the mountain first, but we're all connected. Have you ever seen this in a movie? Or maybe in real life?
And then Isla falls off.
Right, Isla falls, and the next person falls, and we all fall to our death.
Why
Right.
should all be connected?
So, what that happens?
No. What happens is one person falls off, and then you got the next person almost fall off, and they're holding on with
Right.
one hand, but the rest of the people.
And then a
fall
rock
off,
crumbles.
'cause then-
Right, I know. Stay with
then,
just.
Why
Stay
would
with
they all be connected to each
That
other?
happens
That's
all the
so
time.
stupid.
No, it's not, because you're all usually anchored in. So it would be safer, especially if you have inexperienced climbers. This is not about that. Stay with me. So if we're all connected to each other, that's like water. So as Isla climbs up the mountain, whoever's next climbs up, and then whoever's next, because you're all connected, water is the exact same way. So water is connected to itself, so it pulls itself up. So I think this is cool. Obviously, you can tell I kind of get excited about hydrogen bonding. I know that may sound lame to you, but a lot of things can be explained from hydrogen bonding, and I think it's pretty cool. And geckos are cool too, even though they scared the bejesus out of me, because I'll tell you why. I had a honeymoon in Hawaii, and we had a little like thing we rented in the middle of nowhere, and there was like 7 or 8 geckos in the room. But they were like making noises and crawling, and I had never really experienced geckos before, so I was freaked out. I was like, we're gonna go to sleep. They're gonna like, I don't know, bite me and I don't know, crawl in my mouth, my eyeballs. I don't know. I got like nervous. My wife thought I was a big baby. But the point is, I looked into geckos. I'm like, how are they doing that? Hydrogen bonding. So I like geckos because they're like chemistry. All right. So.
Why has like mad geckos in his basement? They're just climbing.
I would like to own one now and they're great because they eat bugs. So if you get a couple, just throw them in your house and they'll just eat spiders and flies and stuff. So, but it all comes back to chemistry, people. That's the point. All right, now this is a video on nuclear chemistry. So we're gonna do 2 things at the same time. We're gonna take notes and watch this. So we're done with the forces. In your notes, write nuclear chemistry. I'm not gonna write it because I need more space. So write nuclear chemistry. And I'm going to let you watch a little bit, then I'll stop it. We'll take some notes, watch a little bit, stop, that kind of thing, till the end of the period. So we only got about 7 minutes left or something like that. A little bit more. But, so that's forces, that's over. Nuclear chemistry. Does anybody remember anything from the video last night? What
Yeah,
makes something?
half-life.
The gold.
Half-life, right.
Remember that.
Good. What's that?
The gold.
The
stuff
gold
that
thing?
you got.
Yeah, I have a little piece of paper over here that says carbon dating. Have we talked about that before?
Yep.
2 carbon 14 atoms that say where have you been my whole life? It's supposed to be have, where have you been, Devin? But where have you been? Because it's nuclear.
Yeah.
No, you're plotting.
Hey, Jake.
Feel the
Cash
pressure
money.
Go.
after watching it. Oh my god, this is the second one
That's
today.
okay. All right, so watch the video.
Shut up.
You
All
need
right.
to make the varsity basketball.
Hey, hey,
This is throwing
Hey.
bottles in a basket.
this is why we're not going to do this anymore because it wastes too much time. If it took like 4 seconds, that's one thing. All right, watch the video. It's from a TED Talk. I don't know if you guys heard of that.
It is only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the
I'm
atom.
gonna stop it already. You don't have to write anything yet. But what he just showed, so that atom sneezing and then turning into something new. What's that called? Transmutation. Good. They call it radioactivity. Transmutation produces radioactivity. So, and I'll explain. He'll explain more.
It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously. The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, a carbon nucleus can eject a fast-moving electron.
Okay. Why, if you picked up so far, why do these elements sneeze these things out? What did he say? Why does this happen? Why is radiation given off? Why are these things changing into something new? He said it. Don't make me rewind it. I'm gonna have to rewind it. Alright.
It's only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the atom. It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously.
Why does it change suddenly, spontaneously? It's not stable. First thing we're writing down in our notes. Nuclear chemistry. Unstable, right? Nuclear chem is the title. Unstable nuclei, that just is plural for nucleus. Unstable nuclei emit radiation. So that's this little part. Oh, hold on.
The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, a carbon nucleus can eject a fast-moving
Okay, so this fast-moving electron is called a beta particle. That's one form of radiation. So the carbon sneezed, it ejected, emitted a beta particle, an electron. So the electron was shot from the nucleus, which is a big problem, and it turned into nitrogen. So what happens is unstable nuclei, underline that, that's the most important thing, emit radiation and
Oh, I know it. I remember this.
turn into a new nucleus. And that new nucleus, parentheses here, is more stable. I use the analogy, if we get really, really sick, sometimes we do this and we feel better afterwards. Sneeze, good. What else? Throw up. My analogy is throw up. Sometimes you throw up. And usually you feel a little better afterwards, maybe not always, but go with me on the analogy, that if you're sick, you get rid of the bad stuff and you feel better. The elements do the exact same thing. They get rid of what's making them feel bad and they become more stable. Not necessarily stable, but more stable. So if we have a radioactive, an unstable nucleus and it emits radiation, it turns into something new. This something new still may be unstable, but it's less unstable than when it started. This may emit radiation, it forms something new. And it keeps doing that until it's finally stable and it stops doing that. Stops sneezing, stops getting rid of the radiation. Okay? So this actually is really important to understand, because if you understand why things are radioactive, where radiation comes from, what makes nuclear chemistry, which is just this phrase right here, it helps you learn the rest of it. Okay? So unstable nucleus, and I'll talk more next week about why it's unstable. We're not done. We're going to keep going here. But let's just continue with the
electron and turn into a nitrogen nucleus. There are two different particles that can be emitted from radioactive nuclei, though never together. The very fast electron is known as a beta particle. If you know a little bit about electrons, you may be thinking, what was the electron doing in the nucleus in the first place? The answer is that a neutron in the nucleus spontaneously changed into a proton, which stayed behind, and an electron flew out as a beta particle.
So I'm not even fully sure, to be honest with you, why this happens. Why that one neutron turns into a proton and kicks out an electron. Physics takes over a little bit there for chemistry, and it's not that easy for even really, really smart people to explain. Not 100%, I don't think. So I don't know why that one would change, but this one doesn't, or this one changes and that one doesn't. But it does. It spontaneously does it on its own, emits that radiation in an attempt to become more stable. So that's what he's talking about. So the electron wasn't really in the nucleus. It was created after this thing changed. That's why nuclear chemistry is kind of weird and very powerful. Lots of energy can be associated with that.
This is not what chemistry has taught us to expect. The nucleus is supposed to be stable. Neutrons don't change into protons, except sometimes they do. The other particle that emits spontaneously from an unstable nucleus is alpha. An alpha particle is 8,000 times more massive than beta, and it's a bit slower. Alpha is made from 2 protons and 2 neutrons. If we trap a lot of alpha particles together, we get helium gas. Alpha is a helium nucleus.
So at this point, I wanted to have you take out your reference tables, but it's going to take too much time, so I'm going to show you. Helium 4/2 and 0 - 1 E. This is alpha, that's beta, way bigger. He said 8,000 times bigger. There's 2 other types of radiation, gamma and then positron. These are all on reference table O, which we will get out on Monday. That's not an 8, by the way. So we'll talk about this on Monday because we're basically out of time. And I guess I'll stop since the phone's ringing. So no homework.